All right, in the second part of this lesson, we're going to go over the squeeze theorem and then talk about two special trigonometric limits. So the squeeze theorem says, formally, that if you have three functions, let's say h of x, f of x, and g of x, h of x, f of x, and g of x, where h of x is always going to be smaller than all of them, or at the most, it may be equal to f of x, and f of x will be always greater than or equal to h of x, but always smaller than or equal to g of x, and g of x will always be greater than all of them, or at the most, it may be equal to f of x. So these three functions are always going to hold this inequality for all x in some interval that's open, and it contains some point c. Maybe like c is just think about a number. Maybe it's 5, maybe it's 10, maybe it's 1.3. Now, so we're going to say this holds except for possibly at that point c itself. Then we can say that the limit, or not, well then we can, well, I'll show you in a second when we graph it, but we have the limit then of h of x as x approaches c will be equal to the limit of g of x as x approaches c, and we'll define it to be L. So their limits will be equal. And then we can also say that the limit of f of x will be equal to that. So we can say that the limit of all three of these will be equal to each other at that point c, even if we don't know what's going on with f of x at c. Now, the point of this is, well, kind of what I just said, we may not know what's going on with f of x at c. There's some graphs you're going to see that do some weird behavior. They oscillate, or they, don't approach some, they don't intuitively approach some number. If you remember some of the examples from the previous lesson, we have that sine graph that oscillates, that would oscillate infinitely, and you would never go towards some number. So when we have functions like that, we want to compare to other functions that we do understand, and then we can actually find the limit at some point in that interval that we're wondering about. So let's draw a picture of what this looks like geometrically speaking. So let's draw our x, y axes. And let's say, remember, g of x is going to be the top always. That's the big greatest function. So say g of x does, maybe it's like this. That's our g of x. And we're going to have our c value. Let's say it's right here. C, we'll draw a dashed line, for x equals c. Now we know that our other graph for h of x will be the smallest. So maybe h of x is doing something like this. And it goes up to that point of g of x at c, or g of c, but doesn't actually get larger. So there's our h of x. And we say that f of x will always be between these two functions. So we'll have f of x, be our third graph. Let's use. I'm feeling purple. Let's do some purple. Maybe f of x does something. Maybe it does something weird. It's always staying between. That's all we care about. That's f of x. So, see, it's called the squeeze theorem because basically f of x is squeezed between two functions that we're going to name g of x and h of x. And we may not know what's going on with f of x at that point c, but if we know what's going on with g of x and we know what's going on with h of x, we can figure out what's going on with f of x by comparing those two. So let's go through an example to really get an idea of how we can apply this. So we're going to look, and we're going to go ahead and show that the limit as x approaches 0 of x squared times the sine of 1 over x is equal to 0. So, here's an example of a trigonometric function that's not easy to figure out at 0, because if we plug 1 over 0 into here, we're going to get some undefined value. But the thing is, we don't know, like, if that's we can't really say that it's undefined, because we know that sine of x is defined for 0, and we know that x squared is defined for 0. So where it's like, is it undefined? Like, we can't really say what's going on. Like, it's not easy to comprehend. It's very abstract. So what we're going to do is go about this by comparing this with two functions that we know this will always be between. So first, let's establish the basis for the sine function that we should know. We know that that sine of x is always going to be between -1 and 1, right? We should know that by now. Sine of x is always going to be between -1 and 1. Now, that also means that the sine of 1 over x is also going to be between -1 and 1. Now, don't overthink this part, because sometimes some students will, because they're like thinking of this x as that same x. Don't think of it that way. Just 1 over x is just some number. It's just some number. Remember, the sine of any number is always in between -1 and 1. We're just kind of establishing, our foundation to recall like how this function works. So sine of 1 over x is always between -1 and 1. So if we multiply this by x squared multiplying by, what's going to happen is we're going to get -1 times x squared. We'll get negative x squared is less than or equal to x squared times the sine of 1 over x. And 1 is going to be multiplied. 1 will be times x squared, so it'll be 1 over x. It'll be x squared. So then we know that negative x squared is going to be less than or equal to x squared times the sine of 1 over x, which is going to be always less than or equal to the positive x squared function. Now, what we're going to do is we're going to make this our h of x, or make h of x equal to negative x squared. And f of x will be this in middle. F of x will be the x squared times the sine of 1 over x. And then g of x will be x squared. Let me outline them so we can make this a little easy to compare. So g of x will be the tallest function, the big function. The f of x will be the middle, and h of x will be the bottom one. Now, the reason we did this is because we know how the function negative x squared behaves, and we know how the function x squared behaves. And more specifically, we know what happens when we take the limit of these functions as x approaches 0. So since we can say that this function will always be between these two functions, if we define that limit for x approaching 0, then we can define the limit of this one. We can say it's going to be equal to all that. So let's go ahead, let's write that out. So the limit as x approaches 0 of h of x is just equal to 0. The limit as x approaches 0 for z of x, for g of x, is also 0. And again, since this is between those, we know that the limit as x approaches 0 for f of x will also be 0. And then we're good. That's all. That's what we're trying to figure out. Now, again, we can't really plug this in algebraically or make sense of it. But let's look at the picture, just to kind of get some geometrical understanding of this. Let's graph our h of x and g of x functions. We know that h of x looks like this, downward facing parabola going through the origin. We know that g of x is just up to the reflection of it, it's a mirror of it, also going through the origin. And f of x, we don't know what it, we don't know exactly what it's doing, but if you were to actually graph it with some technology, you're going to see it does something crazy like this. We don't really, I should make this a little more bounded. Something crazy. It's not easy to to just, figure out by. And I've actually, I've taken the liberty of using my graphing calculator to kind of give you guys a good idea, a better idea of what's going on. So here's the picture of the graph of f of x, x squared times the sine of 1 over x. It doesn't look like this right now, but let's zoom into the center because we want to see what's going on. So we zoom in. You start to see it starts to bounce up and down. It starts to oscillate. It starts to do some craziness. The computer can't even figure out. Let's see what happens if we trace it. Wow. So if you look at this, not even the calculator can answer our question. It says at the point x equals 0. I can't even. Oh man. Menu trace. The graph is having a hard time figuring out what's going on. Earlier was showing that it was undefined. But see, it's super hard for this graph to even figure out what point to graph or what point to go on, what point to to trace on this, because this graph does some craziness. So that's why we use this theorem when it comes to stuff like this. So always graph this stuff if you have a graphing calculator, again, to reinforce your understanding. But now let's look at some other special limits for two trigonometric functions that you're probably going to want to know. So they are the limit as x approaches 0 for sine of x over x, that's going to be equal to 1. And the second one is the limit as x approaches 0 for 1 minus the cosine of x over x will be equal to 0. Now, this first one, if you're in AP Calculus, this is a very common limit that you're going to need to know. So make sure you memorize it and, practice using it, because it's pretty common to have a problem, at least multiple choice. Sometimes we'll have free response problems dealing with this. So make sure you practice with it. This one isn't, I really don't see this one that often, but still know it. Okay, so let's look at how we can apply this. So here we're going to find each of these limits. The first one we have, the limit as x approaches 0, where we have the function or expression tangent of x over x. So if we plugged in 0 into this, we would get, undefined, form. We'll get an indeterminate form. So we can't just plug in 0 because we get tangent of 0 over 0. So what we're going to do is we're going to, be a little clever here. And let's recall that the tangent of x is equal to the sine of x over the cosine of x. So we can rewrite this as the limit as x approaches 0. Now let me try to fix this blurriness. So we'll make it the equivalent to the limit as x approaches 0. And instead of writing tangent of x, we're going to write this as the sine of x over x times 1 over the cosine of x. See, we just broke this apart. We're being clever because sine of x times 1 is the sine of x, and we can just cosine of x times x is just that same thing. So this is just, we're just breaking apart the math because we can apply this limit to here. Let's go to the next line, actually, to make this clear. And let's write this properly so we don't get lazy. We're going to break this into the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over the cosine of x. Oh, let me fix that. And we know we just learned that this is defined to be 1. So it's 1 times, and the cosine of 0 is defined because the cosine of 0 is just 1. So this is just 1 over 1. And so we'll just see 1 times 1. And so our answer will be 1. Now let's look at the second one. Now here we have the limit as x approaches 0 of the sine of 4x over x. Let me put this in parentheses to make it a little clear. Now we again have an indeterminate form because if you plug in 0 into here, we'll get the sine of 0 over 0, which will be, undefined. So we need to figure something else out. Now what we're going to do is we're going to do some little math magic. We're going to multiply this, but not really multiply. We're going to multiply this by a form of 1. So we'll have 4 over 4 times the limit as x approaches 0 of the sine of 4x over x. And the reason for that is using the properties of limits, we can bring this limit into here, or bring this 4 into here. So we really have 4 times the limit as x approaches 0 of the sine of 4x over 4x. Now you're like, well, what's the point of that? What does that do? Well, here's the trick we're going to do. We're going to make 4x equal to another, we're going to represent it a different way. We're going to make it equal to y. And the reason we do this is so that we can apply the first limit here that we learned. Now we know that if if x approaches 0, y approaches 0, so mathematically we're okay. But what this makes it, what this limit then looks like will be 4 times the limit as x approaches 0 of the sine of y over y. So remember that it doesn't matter what we call this variable. Well, whether it's a z or a k or a q, a variable is a variable. As long as we have the same variable, in represented in this way, then this limit will be applied and it will just be 1. So then this will just be equal to 1. So this will just be 4 times 1. I don't know why I did that. 4 times 1. And so it'll just be 4. And there you go.